Hello everyone, this is Cao Shilei from Sakurai Lab, Kyushu University. Today I would like to introduce my research paper, Face Completion with Pyramid Semantic Attention and Latent Codes. Face completion, which can be considered as a subset of image imprinting, refers to reconstructing corrupted face images that miss some regions. This task is the output of computer vision and can be used in many applications. This work is semi-supervised, and we want our model produce visually realistic and semantically correct image, and its result and not only. The exciting face completion approaches can be roughly divided into two directions: conventional and learning-based approaches. Conventional approaches characteristically fill mixed pixels by merging and copying purges based on low-level features like purge merge, and the learning-based generative face completion has yielded great improvements through the adaptation of gains and the optimization of computer hardware. Generative face completion treats the problem as learning an end-to-end mapping from mixed input and to the completed output, which achieves the greater development of face completion. These methods always cooperate autoencoder and GAN for modding. In our paper, we choose the second one. However, face completion is still a challenging task worthy of attention since it's difficult to map the latent codes to photorealistic images and the reconstruction parts need to merge with its input boundaries. See the below picture for example. The repaired image didn't recover consistent and failed to reproduce plausible details. The symmetry of eyes is ignored as well. Here are our framework. At first cause step, we adopt unite and irrepressive snooze methods RTV for well-representing global structures. Then we use the same input in the second training step to train the generative network and get a final result with valid textures. Note that we can employ single network during the testing with its two-step training strategy, which substantially reduces the computation resources. And in our work, we investigate how people bring precise images and propose three contributions. First, we take the repaired attention part into consideration, as our brain did. Our attention layers not only merge or past feature information from unmasked background purges, but also search the similar current reconstructed feature purge. Second, we propose our novel semantic attention feeding block, which applies the attention layer into the pyramid structure. Third, we search for the nearest latent codes in the latent space and composes those multiple latent codes by combining their intermediate feature maps. As for naive attention layer, we need to cut the background and foreground into purges. Then we reshape the background into convolutional kernels and search for the most possible texture purge for the foreground. Finally, we reconstruct the foreground attention layer by using this feature information. However, in our model, we think it's not enough to only consider the similarity between the null purge and the mixed purge. In large holes, mine parameters are likely to erase the currently. For instance, in the case of boys' eyes are covered, the naive context encoder cannot well utilize the symmetry of eyes, which would result in our model lack of continuity. To overcome this limitation, our model believes that we should also take the reconstructed feature properties into consideration for promoting our attention layer. We propose our novel attention layer, which combines the similarity of background properties and the reconstructed parts by computing their weighted sums. The traditional unit was developed for biomedical image segmentation. Now, this architecture is widely used for image processing, which briefly showed in this figure. It contains two pulses. The first pulse is the contraction pulse, also called the decoder, which is a traditional stack of convolutional and mux pooling layer for capturing the characters in image. The second pulse is the semantic expanding pulse, also called the decoder, which is used to enable precise localization using transport convolutions. Besides, in this semantic architecture, the skip connection is introduced to concatenate the features from encoder layer and corresponding decoder layer. Such skip connection keeps it convenient to utilize the information before and after the bottleneck, which is available for image compilation and other low-level vision tests in capturing localized facial details. However, it's obvious that the values of mixed regions in the skip net is useless in the above structure, which causes too much semantic information to be lost. Even if we employed partial convolutional in advance, it's only effective for boundaries of a voice, but the knowledge part of mask is still empty with invalid information. Moreover, a single contextual attention layer cannot avoid high-level semantics, which may cause some distortion and ambiguity. And this to handle the above issues and fully use semantic information, we propose the pyramid structure shown in this figure, which both gradually utilize the reconstructed higher-level semantic features to instruct the low-level host filling process and replace the invalid whole feature in skip connection layers. Especially, once a compact latent land, we apply the attention layer to the pyramid structure in order to use high-level contextual information to fill whole regions of low-level encoder feature maps. We repeat the attention layer progressively from the bottleneck layer to up and employ shortcut methods to fill mixed regions in their feature map. These fully filled encoder feature maps are concatenated with the corresponding decoder feature by skip connection, which can avoid the transmission of invalid information in whole regions of encoder feature maps. When we use scan for recovering an image, the matrix is compressed into the latent codes. Both the compression and recovery process are difficult since we need to fully use the latent codes to representing the high-dimensional distribution of the complex real sign. Thus, the generation height is easy to lose some point information and recover blurry and over-smoothed textures. Inspired by Stegan, we built a reference site that contains latent code mapping by completed face images. After we decoded the masked image, we search for the nearest latent codes in the reference site and combine these multiple latent codes by composing their intermediate feature maps. Such an over-parameterization of latent space greatly improves the image reconstruction quality, especially beneficial for large hole filling. However, it's still a big problem to integrate multiple latent codes in the generation process since the use of latent codes directly requires complex decoding. Simply linearly combination of latent codes tends to produce a minimalized image with extremely twisted, especially as shown in figure. We search for the nearest latent codes in the reference site first, and combine these multiple latent codes by composing their intermediate feature maps. The decoder can be understood as decoding that without cross-pointing special features separately for further composition. The adaptive kernel importance scores defined for align semantics. Our model is trained in semi-supervision manner. In Constance, we design our loss function specially. We adopt the node-one loss, the TV reconstruction loss, the procedure loss, the adversarial loss, and we design our overall loss function specially like this. Therefore, we can stably train our game to produce high-fidelity face images. Here are our experiment environment. Our model are implemented in the Ubuntu and PyTorch, run in the hardware of Novender GPU. And this is our experiment result. The x-axis represents number of iterations, and the y-axis represents no-one loss of image. We can see that the no-one loss steady decrease and trend to be convergence. For further evaluate the reconstruction ability of our completion structure, we carry out object removal experiments in user scenarios. This picture shows some instance of application using our completion model. Here, we removed the bird, mask, sunglasses, earrings, height, and watermarks respectively. And this is our result demo. There are the examples of our face completion model on Tab A. The first line shows the input images. The middle line shows the ground truth, and the third line shows our completion results. The speed means the time we need to address an image. And I think that it can show that our model can work well and didn't need too much time to process an image. Also, we have some comparisons with some state-of-the-art baselines and the ground truth on Syllable A. And we can see that our model can handle compilation issues better since we are more vivid and plausible, as well as easy perceived. And for more comparison, we randomly select 20 images from Syllable A datasets centering hosts for each image to make comparison. And we can see that no matter what evaluation matrix, the no-one loss, no-two loss, SSIM, or PSNR, we can see that our model outperforms the others. However, we have to admit that we need more pre-training time for our model. So this is our disadvantage. In my future work, I will try to solve this problem like selecting core attention layers for pyramid structure instead of apply p block in every layer. Also, in my future work, I would like to combine our model with natural language processing to make a small program that directly inputs the text of unwanted object and remove it using image completion technology. And we design our model like this. We just input the text of remove eyeglasses and we can output an image, face image without eyeglasses. And we think it was useful in real world. That's all. Thank you for your listening.